I want to welcome you to my lecture today. Today we are actually starting chapter 11. But you know what? Uh, there's going to be some extract from chapter 10 as well. And that was why I call it chapter 10 and 11. But before I get started today, I'm basically going to release my rubric for practical 3 today. But I waited before now for almost all the class to get that. Now everyone now has data set based on my record, and today I'm basically going to release a rubric for practical 3. Okay, so today, like I said, I want to walk you through what we call additional topics in logistic regression model. And of course, in the outline, I'm going to walk you through what we call the likelihood ratio test. We started on Friday. And of course, I'm going to start from there today. You're going to have opportunity to compare between models under logistic framework. I'm going to say that again. You're going to have opportunity to compare between nested models, okay, in the framework of logistic regression, just like what we did in linear regression, where we have a way to, compare models. We're also going to do that with the logistic regression model using what I call the likelihood ratio test, the LRT. And today, I'm also going to walk you through steps involved in analysis of logistic regression model. In case maybe there is one of you who is working in this area for your project, you're basically going to see the step. If you want to use logistic regression model, of course, you're basically going to see the steps that you need to undertake where you want to do your analysis. Now, let's get started. First, I want to show you the model because it's very, very important to specify your model. That is a preliminary, part of the preliminary investigation in statistical analysis is basically to, specify model. Of course, what I'm showing you now is logistic regression model, one in a logit form. Of course, I told you, what do I mean by logit form? It actually means the log of odd ratio. Okay, the log of odd ratio. I remember the other time, give me 1 second. Yeah, the other time I told you I can write logit of pi or log this divided by that. It's the same. Okay, I just wanted to take note of that. So what I'm showing you now is a multiple logistic regression in logit form and in probability form. I just wanted to take note of that. But let me tell you today, I'm basically going to walk you through some examples. I have 2 examples on the slide, one from education and the other one from bank loan. And there's another one I'm going to add in the course of my explanation, which is how can we actually use logistic regression in a criminal justice system. I'm going to add that today as well. You're basically going to see how logistic regression model can actually be applied in a criminal justice system. Okay, but you know what I'm trying to show you now, just the specification of logistic regression model, both in logit form and in probability form. Okay, now, if you want to compare models within the logistic regression framework, of course, we're basically going to use likelihood ratio test. And of course, in the likelihood ratio test, what are we actually testing? I want to tell you now, if you look at what I'm trying to show you, the hypothesis that I'm trying to show you now is, if you look at the non-hypothesis they show, it's trying to say all slope equal to 0. That hypothesis is basically supporting intercept model. I'm going to say that again. Intercept model is basically model without predator. Okay. But when you look at the alternative now, it's trying to say at least one of the slope exists. And of course, the test statistic that we basically going to use is what we call deviance, which is, you can take a look at the G, which is the difference between the -2 log LO. The LO is the likelihood when the non-hypothesis is true, and L is the likelihood when the alternative is true. But let me also tell you, we can also use this to test between a reduced model and a full model. I'm going to say that again. So if you take a look at what I'm trying to show at the bottom, okay, the mathematical way of expressing that is what you have at the top. I'm going to say that again. What I specify at the bottom, where I have reduced model versus the full model, okay, the mathematical way to express that is what I have at the top. Take a look at that. Okay, so the likelihood ratio test is basically used to compare nested models, a logistic regression model. Of course, I walk you through this the other time when I actually computed a reduced model and a full model. And you know what we did? We subtracted the residual deviance, right? If you check what we did in the last lecture on Friday, we subtracted residual deviance of the two model, and we computed p-value based on that. And of course, the p-value was what we used to judge whether we should actually reject the reduced model or not. Okay, I think I walked you through that on Friday. But you know what I want to walk you through today? I want everyone to be focused, and you need to ask questions if you need clarification. I need you to watch, I need you to focus on the board. Now, this is the question. I walk you through on Friday how to compare two models. But what if in a situation where we basically want to have more than two models? We basically want to be selecting predator into a model based on the nature of the p-value. And that is basically going to be called the multiple nested LRT. Okay. And I want to apply now to education. And I want us to listen now. I want us to be focused. Ask me question. You pay for the service. You deserve to be served better. Okay. On the if for instance, if I basically want to look at the effects of GPA, MCAT, and whether the applicant is a female or not on acceptance into medical school, I wanted to take a look at what I have on the board. You know what I have here? I've extracted the the residual deviance, and when you run a logistic regression model for a particular model, you're actually going to have no deviance and residual deviance. If you check the outputs, I'm going to say that again. You're going to have non-deviance, and you're going to have residual deviance for a particular logistic regression. This is going to come as part of the output. You know what I've done here? When I look at the effect of GPA on acceptance, this is the residual deviance. That is the full deviance. The difference between the residual deviance and the full deviance is given, and I computed the p-value. I want you to follow what we did on Friday on how to do that. Now I do the same thing for MCAT. I do the same thing for FEM. Now, I want you to see out of these three predators, we basically want to say the one that we basically going to consider in our model. If you want to choose a predator into a model, you got to choose a predator that have a low p-values. Now, when you take a look at what I have here, when I compare the GPA with nothing, because they not you are comparing each of these predator with an intercept model, and what you have here, which one actually give us the lowest values of the p-value? As you can see, it is GPA. Look at that, GPA out of each of these predictor. You know what I did? This is like running a three separate logistic regression model where in each circumstances or in each situation, I use GPA as a predator. In another situation, I use MCAT. In another situation, I use FEN. And this is what I come out with. I come out with three p-values. And of course, based on the fact that we got the GPA has a low p-value among all the predator considered, I actually choose GPA. That was why I have this model here. That was why I have this guy here. I'm choosing GPA based on the fact that I got a lowest p-value. I'm not going to end it. I'm not going to stop there. Okay, I just selected GPA now. Now look at what I did here again. Now I know that GPA actually work, right? You know what I want to do? The first model here, I actually consider a multiple logistic where I added MCAT to GPA. If you look at the first model here, it's multiple logistic, while each of these is simple logistic. Each of that. It's like I run the three separate models now. Why am I adding MCAT to GPA? Because in the first instance, I've already selected GPA because the GPA has the lowest p-value. But you know what I want to do now? I basically want to see a competition between when I added MCAT to GPA and I run that, and I run FEM separately and I run GPA squared separately. The GPA squared, why am I considering the GPA squared? Maybe since the linear aspect of the GPA is significant, we also want to investigate whether the quadratic aspect will be significant as well. But I want you to take a look at the p-value here. And as you can see, the GPA square is out of it. Why? Why is the GPA square is out of it? The p-value is very, very high. It's 0.308. The GPA square is not needed at all. We don't need quadratic. But when you look at the GPA plus MCAT and the FEM, you're basically going to see that one has is 0.090 and the other one has is 0.89 to 2 decimal. They are the same. If you look at that, to 2 decimal, they are the same. Then it means I'm basically going to go for the GPA and the MCAT. And that was why you can see it in the new model that I have now. I got a GPA and MCAT in my model. That's what I have now. And you know what? You can also consider, if I were you, if I want to conduct this research, I'm going to take this as one model. I'm going to have another model where I'm going to have the FEM. Because you know why? The FEM is also having a p-value, that is more or less the same as the other one. Now, what do you think I've done here? I'm trying to go stepwise to select predator into my logistic regression model using the likelihood ratio test. Now, I told you, finally, we're also going to consider the FEM. When I run a separate model again, then I realize that the FEM needs to be included. Therefore, in our final model, you're basically going to see that we can actually compare this one, the complex one, with the FEM, with the one without FEM and see which one is better. Okay, we do a lot in model selection. Okay, so that is that on how to go about that. Okay, go ahead.
Why are you selecting, even though like the lowest p-value, it's still like say we're at the significance level 0.05, like 7.2, still above.
Look at me. You are very, very intelligent. If I heard it very well, you said, why am I selecting that despite the fact that the p-value is greater than 0.05? That's your question, right? That's a that's a very good observation. You know, we don't select until we don't use that threshold. We relax that threshold for a while. You know why? Because if you take a look at what I have here, you're basically going to see that the GPA square has a very huge p-value compared to the other one. If you look at the 0.09, the 0.08, they are significant at 10%. Because, we have been using the standard 5%, 1%. At times, we could use 10%. And these are also very close, even if you want to use a 5%. And that is the reason why what we're going to do now, let us consider them as part of our model. But this is not the final model. You know what we're still going to do? Like this one here, we can compare with this one here and see which one is better.
Okay.
So once again, look at me. That's a very good observation. You're welcome. Now, I want to go into now. Let me now. I gave some codes here. You know the way the other time when you are comparing two models, you for first do manual way of like, getting subtracting the residual deviance of the two model, you get the p-value, and that's taking forever. But you know what I want to show you now? Easy arrow code to go about that. Now I want us to make use of this now. I want to have an example of grades. What determines grades? Student grades, right? Age, travel time, study time, absences. You know, maybe the midtime grade, the midtime one grade, the second midtime grade, or the final grade. I'm talking about the final grade. Now we now want to use a likelihood ratio test. We want to test between using a simple model and a complicated model. I want you to pay attention now, please. Focus on the board. I want you to pay attention now. Okay. Now, when you take a look at the simple model, I'm trying to see the effect of absences on final grade. Just like what I was complaining the other time that I've not been seeing some student in class. What is the role played by absences on your grade? Now, the first model, that's a simple model. This simple model, we also call it nested. Simple, you can call it simple or you call it nested. Okay. Now, against a complicated model that I'm also going to call, you can call it complicated model or you call it a complex model. It's the same. Okay. Complicated, complicated, complex, they mean the same. Now you know what I'm trying to do in the second model, right? I'm looking at the effect of absences and age. Look at that. On the second model, absences and age are predicted. But on the first model, absences, of course, you can see the simple model is nested, right? Oh my God! If you want to do this, you just write LRTST nested, complex. Here, since we are calling this simple, it's going to be simple, complicated. Okay, it's going to give you a result. Where's the result? Oh, the result is here. Very easy way. That is easy code. Now, what happened now? Look at the p-value. Under the non-hypothesis, the model one is the simple model. You know that, right? The one we call the nested model. Under the alternative, the complicated model is their model two. Now, the non-hypothesis is going to tell you model one, the simple model is appropriate. Why the alternative is going to tell you, complex model, the complicated model is appropriate. Now take a look at that now, based on the p-value that we have, 0.0161. That is greater than, is 0. Sorry, that is less than, is 0.05. When it is less than 0.05, what are you going to do? You're going to reject the simple model. So which means what determines the final grade is absences and age, not only absences. That's a simple R code to go about that. I have another example now. This time around, my simple model has study time, first grade. Okay, I got two predator in that, and in the complicated model, I got study time, per one grade, per two grade. Look at that, more complicated. Look at that. Okay, you could have situation where the simple model could be one predator, a simple model could be two predator. But what makes it simpler model is when you have more predator in the complicated than simple. Okay, at the end of the day, just gonna write LR test. This is likelihood ratio. N likelihood ratio test of that. Oh my God, it's gonna give you that result. What is it telling you now? The complicated model is more appropriate because the p-value is less than the 0.05 level of significance. Now, this is how to compare models, how to compare logistic regression model using the likelihood ratio test. This is an easy R code to compare between two models. Now, you know what I want to walk you through now? Steps involved in analysis of logistic regression model. What are the steps? One by one steps. But you know what I want to do now? I want to use a bank data example. In this data, we have 10,000 individuals. They happen to be customers in this bank. And the bank already have information about their customer, about the 10,000. And this information call across default. You know what I mean by default? Default is that is a failure to meet, obligation of a loan. You apply for loan and you fail to meet your obligation. Maybe you apply for student loan, you don't pay back. Or you apply for mortgage loan, you don't pay back. That's what we mean by default. This particular bank has, they have data set where where some of their customers default and some did not default. But you know what? This particular bank wants you to develop a model, a classification model. They're going to develop a model and they're going to use that model to reclassify new customer. If they put it to consideration, they are predator. They want to predict. They want to know whether this particular customer is basically going to default or not. Using the model, but you got to use the model based on the existing data set. Now, the data set has students, whether you are a student or not, that's categorical. This particular bank have, some of their customers are students, some are not. Then the balance on your account. We actually want to see the role play by the balance on your account to the default. Then your income as an individual. Also, we also want to look at the effect of that. But you know what? If you want to have access to this data set, you need to load a package called ISLR. Okay, you can load a package, then you're going to have access to the data set. But you know what? What I'm trying to show you now, out of the 10,000 customers in this bank, no default. 9,667 individuals did not default. They pay back. Why 333 customer defaults? Okay. Now, out of in this place, 7,056 are not students, while 2,944 are students. Okay. And of course, the balance, the minimum balance 0, the maximum is $2,654.03 or maybe 30 cents. And this is the income. The minimum income is 772. The maximum income is 73,554. Of course, this guy here is telling you got 10,000 customers in this bank. Now, step one, when you want to run logistic regression model, you need to disclose your data set. We want to see your data set. That is going to be step one. And you're going to do all this. For those of you who want to write projects using the logistic regression model, we basically want to see your summary. This is what we call descriptive statistics. You need to describe your data. We want to see, is it variable? What is a minimum? What is a maximum? You can see we got 4 variables here. 2 are categorical. Default and student are categorical. They got 2 levels. While the balance and income are quantitative. They are quantitative. That is why you have 5 number summary. I mean, you got 6 number summary of them. Now, step 2. What we've been doing before. We run the logistic regression on the entire data set. What I want to disclose now is not in that textbook. But why am I disclosing that? I told you what happened today is not in the textbook we're using. Every day by day, different things happen, right? Textbook is static. And that is why we need to continue to remodify, a textbook. That's why you're normally going to have new edition, right? But this is the way we do logistic regression now. The way we do logistic regression now is we're actually going to split our data set into training and into test. I'm going to say that again. We're going to split our data set into training set. We're going to train our model with some significant part of the data. And we're going to use the model, to predict the test. And you know what here? I'm actually using 70% because the significant part of the data need to be committed to training. Why 30%? Some use 80 to 20. Now I'm using 70 to 30. But just make sure the significant of the data set is committed to training. Okay, now that is what I've done here. This is the code. If you follow all this code, that is what I mean. Okay, 70, 30, train. I'm splitting the entire data set into training set and the test set. Okay, now we're going to use the training set to build our model, and we're going to use the test set to validate our model. Okay, now that's all we have. That's the code. Now the step 3. We now want to fit the logistic regression model. But like I said, you basically, what data are we using here? Train. Look at that. To build the model, you use the train data to build your model. Okay. Now this is a model. This is the result that I got. This is not on the entire data set. This is on the train one. 70% of the data set is committed to training. This is what we have. Now, this is what we actually, going to use to, to set up our model. Now, right now, balance on the account is significant. That is true. That is expected because your balance on your account, actually depends on, will determine whether you are going to pay back or not. Somebody who have a negative balance or very small amount of balance on the account may not pay back. You know that, right? It is significant. Look at that. The balance on the account is significant. Okay, the income is not significant. We have people who have either high income or low income. They may decide not to pay back. Okay, and whether you are a student or not, it's not that significant because they have a 0.0843. Take a look at that. Now, this is a model. Okay, now when you take a look at this model, this is just to, what are we trying to say concerning the balance? The balance here, the estimate is 0.0059 is what I'm trying to interpret. Don't forget, I told you whatever that came out from the logistic regression model. We call them log hard estimate. Don't forget, log hard estimate. Log hard estimate. And if you want to see the way we're going to interpret the one that has to do with the balance, okay, the 0.0059, look at the way it is interpreted. For example, if 1 unit increase in balance is associated with an average increase of that in the log hard of the 14, the log hard of the response. Don't forget, not just the response. I told you in the log hard of the 14, and the fact that the p-value is very, very small actually show it is significant. Okay, now the next thing that I want to do now, we have a model in place, right? This is a model that we have in place. The next step is going to be, how do we assess the model? How do we know that the model is good? Don't forget, this model, we only use the training data, 70% of the data set. Okay? Because do you know why we need to split? Don't forget, 100% of customers here, we already know their status. And if you really want to know whether your model is good, you know what you're going to do? Use 70% to build the model. Use the remaining 30% to evaluate the model, where you're going to make a prediction. Your model will predict. Compare what your model predicts with what happened in reality, which I'm going to show you. Okay, now one of the way of assessing model fitness, in the linear regression model, we use R square, right? We use adjusted R square, right? But we don't use that in logistic regression anywhere in the world. You don't use R square for logistic, but logistic has its own special R squared that we call MC Faden R squared. MC Faden R squared. And the MC Faden R squared, if you take a look at it, we say very close to zero indicate that the model has no predictive power. And in practice, value over is 0.4 indicate that your model fit the data well. Okay, I just wanted to take a look at that threshold. Over is 0.4. Your model is fantastic as far as the MC Faden R square is concerned. But how is it calculated? What package do I need to load in R? Oh my God. If I want to have access to this, I need to load a package called PSCL. And after that, I'm going to do PR2 model. Then I'm going to have this. What did we say the other time? We said over is 0.4. That means that model is fantastic. But right now, we got a 0.47288 for our model, which means our model has a very high predictive power. It is not all statistical model that has a very high predictive power. But how do you check for that of logistic regression? You calculate the MC Faden R squared, which is calculated this way. This is just a code. Okay. Now, the next thing I want to talk about now, can we talk about variable importance? The predictors that I use in my model, how important are they in terms of magnitude? We got a way to do that. You need to install a package called Caret if you really want to investigate variable importance. Now, right now, you're going to write VAR IMP model. Oh my God, which variable is important? It is balance. Look at that. And don't forget, the balance was significant. The more the magnitude of a predator, then the more it is important. Take a look at that. After balance, the next is going to be students, whether it is student or not. And the last one is income. Take a look at that. Because you could have so many predictor variables, and you basically want to see which of them are important. That's what we call variable importance. Now, I told you the other time, one of the assumption of logistic regression model is that the predator variable should not correlate. You know that, right? I told you the assumptions are there should be linear relationship between the logic of the response and the predator. That's number one. Number two, I said there shouldn't be any outlier and no multicollinearity. Now, what do I want to do now? I want to investigate multicollinearity because I got more than one predator. Then I need to load a package called car, CAR. Then I'm going to do VIF. Of course, you've done that before. Oh my God, look at that. None of this is up to 5 threshold. You know, we got a threshold, right? 5. If it is more than 5, what happened? Multiculinary exists. But right now, there's no multiculinary problem. The model is good because none of this has a threshold of 5. Now we're going to go to the next, the step 4 now. You now know what you want to do now. We want to make a prediction with our model. The essence of building a model is for the purpose of making the prediction. From these particular individuals, if somebody have a balance of 1,400 with an income of 2,000, and I want to predict for students or no students, I want to have 2 predictions. Okay, I'm going to say this again. I want to predict for 2 individuals. Each of them has the same balance of $1,400 in their account, and their income is 2,000. This is the code. Now, when you take a look at one here, yes, for this for students, no students. This is the probability that they will default. That person with a balance of 1,400 in account and an income of 2,000, this is the probability that they're going to what? For students, this is the probability. For no student, this is the probability, which I wanted to see now. For student, this is the probability. For no student, that is the probability. And because of that, I said the probability of an individual with a balance of 1,400 and with an income of $2,000 and a student status of yes has this probability, okay, of what? Of the 40. Take a look at that. Okay, and somebody that is not a student in that particular band has this probability of this defaulting. Take a look at that. Who is more likely to default? Can somebody tell me? Looking at the probability, who is more likely to default between student and no student? Who is more likely to default between them? Who can tell me? Student or no student? Who is more likely to default? Can somebody tell me? Extra credit? Oh, somebody just. Oh, no student. Okay, send a message to me for extra credit. Somebody who said no student, because no student has more probability. This value here is 0.04. It's more than 0.02. Somebody who is not student is more likely to default. Okay. The last model 5, step 5, model diagnostics. And what do we do in model diagnostics? We basically want to set up a threshold. You know, some people in classification, they use 50%, above 50%. When somebody have a probability of default above 50%, they're going to believe that that person can default. But we have a code to calculate the optimal value for that. This is the code. Okay, this is the code. And this is going to tell us anything above 54 point something percent, okay, we're going to classify that person as a defaulter. But I told you the conventional one they use is above 50%, but you need to be able to figure out, you need to find the optimal cutoff probability to use to maximize accuracy, which is what I've done there. Now, when you've done that, the next thing you're going to do now, now I want everybody to pay attention to this, which we call confusion matrix. Now, I'm going to write something now. I wanted to look at the board. You know what confusion matrix does? The confusion matrix will give us a table. You know, do you know what do we use in the confusion matrix now? Test. We use the remaining 30% data set to construct this table. And I want to tell you what this table represents. Predicted, actual, okay, positive, negative, positive, negative. Take a look at this. Now, this is true positive. True positive. Take a look at that. This is true negative. Okay. This is false positive. This is false negative. Okay. You know what this guy is trying to tell me now? This is equal 2912 64 21 39. Now, I want to explain this. Now, I needed to focus on the board. What the Confucian matrix is trying to tell me now. This is the actual number of positive. And your model, the model predict 2,912. This is true positive. Now, the actual number of negative 39, the model actually predicts 39. If you take a look at this, okay, if you, this plus this is what we call, you know, when you want to talk about accuracy of your model, the accuracy of your model is true, it's a correct assessment divided by total assessment. Total assessment. If I want to know assessment, if I want to know the accuracy of your model, so which is basically TP plus TN divided by all of them, which is 10, you understand, divided by all of them. So which is 10,000, right? So which is TP plus TN plus FN plus FP. This is the accuracy. If you want to know the model accuracy, like now, if you want to know your model accuracy, you're going to do 2912 plus 39 divided by all of that. That is the accuracy of your model. Now, the next thing, and that is what you have here. Take a look at this now. We want to find, in addition to the accuracy, we want to find sensitivity. What is sensitivity? The sensitivity is the ability of your model to detect a customer that defaults as being a defaulter. This customer defaults and your model can detect that. That's what we call sensitivity. I'm going to say that again. This customer, nature knows the truth. He actually defaulted. Can your model catch that? The ability of your model to catch that is what we call sensitivity. Now, the sensitivity here of this model is this, which means the sensitivity of this model is low in terms of catching the defaulters. But what about specificity? The specificity is the ability of your model. If somebody is not going to default, then your model should be able to detect the person not to default. That is what we mean. So if I want to write that now, I'm basically going to write, I'm going to write this. I'm going to say sensitivity, okay, true positive divided by total positive. Okay, when I say true positive, I mean true positive. When I say total positive, the total positive is going to involve false negative. You know that, right? Then the specificity now, okay, is basically going to be true negative, okay, divided by total negative, okay, which is going to be true negative divided by true negative plus false positive. Look at that. You can, so that is, this is a code for that. Oh, this model is very, very good in detecting those who did not default, and he was able to detect that they did not default. How many times? 99.28% of the time, he was able to do that. And I told you something the other time about classification error. I told you there's no model that is the best anywhere in the world. What I mean, according to George Box in 1986, model, we want to use model to capture reality, but model can never give us exact reality. Now, when you are classifying, what is the error of classification? the error of classification is this. How do I get that? You know what you're going to do? If I showed you the other time how to get okay, now let me go back. You're going to see now here. Do you know that this guy and this guy, they are misclassification? If you add this to this, 64 to 21, if you add 64 to 21, divided by the whole thing, that is your misclassification error. Because this is like your model predicted 64 to be positive, but in the actual sense, it is negative. There are 64 that occur, 64 out of the 10,000 customers. And out of the customers, sorry, I made a mistake. Not 10,000 customers. We're using 30% for test, right? What is 30% of 10,000? So we're using 30% for test. Okay, now when you take a look at what we basically have, I think 30% of 10,000 should be 3,000, right? Okay, so the whole of this is 3,000. We're not using the entire data set. So the error of misclassification now is very, very small. Look at that, 0.027. Before I go today, I want to give an example again in criminal justice system. In criminal justice system, there's something that we call recidivism. I don't know for the recidivism. You know what I mean by recidivism? It's like, what is the ability of a convicted criminal to reoffend? Okay, ability to reoffend, because the courts, they don't just give judgments. They look at some, they call it aggravating factors, because they want to see whether they should increase the sentence or they should decrease that. You may want to look at the probability. Okay, why? Your response variable could be 0 or 1. Okay, here, reoffend, not reoffend, not reoffend. And you may want to look at the variables, the predictor variable that corresponds to that. Prior offenses could be one of them. Like, we also call it prior counts. How many times has he done that before? Will be put into consideration. What about the age? Do you know that we can fit a logistic regression on this to classify, suspects that are already guilty before the court of law, okay, on whether they're going to reoffend or not? So the judge don't just take a decision. After they found somebody guilty, they could give the person a lower sentence, and they could give the person, more. They could extend the sentence, depending on some factors. And that is the reason why at times when the judge take a decision, and somebody going to say, oh, why do they give him 5 years? They're supposed to give him 15 years. Or why do they give him 15 years? It's supposed to be 5 years. They consider other reasons, other factors. And they use that a lot in criminal justice system. This is where I'm actually going to stop today. Like I said, today, watch out for practical 3 rubric. Make sure you stay safe and have a lovely day. Bye for now, everyone. Thank you too. Make sure you stay safe, okay? Yep.